And welcome to part 4 of the review videos for AP Physics. We're continuing with our question about potential, an electric potential around a system of point charges. So in parts A and B, we were looking at the potential at this particular point right here, and then what that meant about like the change in kinetic energy as it moved from here to really, really far away. What we'll do in parts C and D is look at the potential as a function of position along the x-axis. And C in particular is going to want to know, is there a position where the potential is 0, other than infinitely far away? All right, well, let's make some room for all that stuff. Last year, we did a lot of questions where we graphed out what the potential was as a function of position along the x-axis. And if you recall, that actually is usually the easiest way to work out something like part C. You kind of have to do it anyway, and then you would have to do a lot of algebra if you weren't going to solve it graphically. But if we learn how to do it graphically, then we can make the calculator do the algebra for us, which is going to be a lot nicer. Okay, so let's look at that. If I want to make a graph of V versus X position, I've got to come up with functions for the potentials due to each of those point charges at some arbitrary position. I'm going to use the same dot, but now instead of it being some particular distance from this, I'm just going to say it's x away from this one. So I'm using this as my origin. I'm saying this point, wherever that is x away from it. All right. And that means that this one and this one are going to be something in terms of the Pythagorean theorem away from it, which would be the square root of d squared plus x squared. All right. So then if I write out what the potential is due to those three charges along the x-axis, I would have, well, let's see, due to the two positives, 2 kq over square root of d squared plus x squared. And due to the negative charge, minus kq over x. And if I want to make a graph of it that looks correct for both sides of the x-axis, meaning both to the right and to the left, I'd need to slap some absolute value signs on that. All right. Now, if you want your calculator to actually graph this and give you the right shapes for things, you need to plug in values for k and q and d. We don't have any values, so I'm just going to make believe that k times q is going to be 1. Whatever. It doesn't have to be, but if I don't have particular numbers, I can't exactly just make things up for it and go with it. So I'm just going to say they're equal to 1. Okay. So 2 over, and then I'm going to say, how about d also equals 1? And what this will give me is the correct shape for the graph, even if the y values aren't necessarily going to mean anything in particular. All right, and then minus 1 over absolute value of x. And we'll say y equals. All right, and then it will graph that out for us when we dutifully type it into the calculator. Okay, you should dutifully type it into the calculator to make sure that you're able to make this work. And if I graph on, both sides of the y-axis here, I would get something that looks like this. Kind of like this. Okay, so that's what it would look like on that side. And then it's just going to be a reflection of that on the other. Okay. All right. Now, what all does this tell me, and why should this make sense, and how could I come up with a graph like this, even if I didn't want to go to the trouble to like type it into my calculator? All right, let's start with that last part. How could this be the right graph? Let's start with that. Well, first of all, let's start at infinity. The potential is always 0 infinitely far away. So I know that whatever else it does, it's eventually going to go down to 0. I also should be able to think about the fact that if I get really close to the negative charge here, the potential has got to dip down to negative infinity. The equation's kq over r. If you're close to a negative charge, it gives you a negative potential. And if r is a really teeny tiny number, then that gives you a very, very negative potential because you're dividing by a very small number. Okay. All right. So negative infinity, and then goes to 0, way far over here. In between here, since we've got 2 positives and 1 negative, 2 things have got to be true. Number 1, at some specific point along this axis, the potential has got to hit 0. And second, the potential has to end up at some range of values in positive territory. And I can say that for sure because when we did part A of this, the potential was a positive number, right? So somewhere at x equals 3/4 d, like there, the potential was a positive number. But if I get too close, it goes to a negative number. So that means that there's some specific point where the potential is exactly 0. Beyond that, it's positive. And then it eventually dips back down to 0. Okay, so the shape then ought to look something like very negative potential here, 0 somewhere around here, up into positive territory, and eventually taper off down to 0. That's what you're seeing in this graph right here. And then, of course, the reflection of it, because we don't have any other charges over here that are going to mess with it. If you left off the absolute value sign, this half of the graph would be screwed up. That's all that would happen if you left that off there. Otherwise, you would graph this correctly. Okay, well, there's part D. There's our graph of v versus x. If we want to find a position where the potential is equal to 0 other than infinity, that's right here. There it is. I found it. Your calculator can specifically solve for it. If you were to work out the algebra and such, it comes out to d over root 3. The way that that's going to look on your calculator is, since you replaced d with the number 1, the answer is going to be 1 over root 3. It won't give that to you as a radical. It'll give it, let's see. Root 3 is about 1.73, so the calculator answer is going to be something like 0.57. 0.57, I think it's like 573 or something like that, but let's just go with it. D. Or the algebraically derived answer would come out to be d over root 3. I'm going to pause the video and do the algebra on that real quick, just so you can see how that works out. And there it is, as if by magic. All right, if the potential equals 0, then this term equals that term. And if you wish to ponder the algebra there, then you can pause the video and do that in your own time. Okay, I want to look at one other thing, and this is not a specific question that I asked here in terms of what I wrote down, but there's 2 other things that we could talk about here. Number 1 would be if we go back to this this charge that we put at x equals 3/4 d, right? And we wanted to know what would actually happen to this charge, which way would it go, and that sort of thing. It's a little bit hard to say for sure. The way that we talked about it in part B was, yeah, it'll go to negative, or all the way to infinity. Well, that's not necessarily true. If 3/4 d is like here, which it probably is, that point right there is, you'll notice, on a part of this curve that has a, well, it's a positive slope, okay? But potential, if you recall, or sorry, electric field, if you recall, is the negative derivative of potential. Electric field is the negative derivative of potential. So what that means is the slope here corresponds to the value of the electric field. And if you include that negative sign in your calculation, what it's going to tell you is that the electric field at that point is to the left, meaning towards the negative charge. So actually, if we put that charge little q right here, it wouldn't go over this way. It would get sucked back towards the minus q charge. Okay, and therefore we wouldn't actually, in this simple circumstance, be able to calculate a final kinetic energy because it's going towards a potential of negative infinity. It can't actually reach infinite kinetic energy, but that's what our calculation would come up with here. Okay, which has to be a little bit wrong. All right. Second thing related to this fact right here is if I wanted to know where the electric field was 0, that would be a really difficult, really impossible thing to work out algebraically. It might be possible, but my first guess is it would not be possible to work out where the electric field is 0. And if it is possible, it would be after something like a good half an hour of algebra, which I don't want to do. Where the electric field is 0, though, can be easily determined from this graph. Using this fact here, think for a moment, right? How could I find out where the electric field is 0? It would be by looking at the slope. This is saying that the slope of a potential versus distance graph is the electric field, or the opposite of that is. That means that something like here, the electric field is going to be 0 because that's the maximum. Okay, so anytime you find a local min or a max in a graph of potential, that's going to be a spot where the electric field is 0, and that can most easily and conveniently be solved for by your calculator. Okay. All right. Well, I think that's a good series of 4 videos for you. So if you have any other questions related to your homework, we can handle those in class when you return. Or send me an email, and I'll be happy to give you some kind of a response. So hope this helps, and I'll see you guys when you get back from senior service.